All right. So last time we talked about heat traveling. We talked about refrigerant. Well, we've been talking about how refrigerants work, boiling points, and all that kind of stuff. So today we're going to try to start tying that into actually how an AC system works. This is where it gets, hopefully, it starts to come together, but at the same time, this is where it can get pretty complicated. Because honestly, we can't see what's going on inside of a system most of the time. So you kind of have to understand the theory of it and understand what's going on. But um, once you understand how the system is actually working, it makes things a lot easier when it's not working that way. So that's why we try to go, spend a lot of time on, what it's doing, why it's doing it, what can impact it. If something's not working as it's supposed to, how's that going to affect it? So um, we'll start with this slide right here, or this picture. You all should have access to this as well. But this is probably as close to a cutaway or a breakdown as we could get as far as an AC system, outdoor unit, indoor unit. So you can see we've got your outdoor unit over here, your indoor unit on the right, or your air handler, as we'd call it. It could be a furnace as well, just some sort of AC system that has a blower and a coil. So um, without getting too in depth yet on what's going on inside of the system, remember, what is the purpose of an air conditioner? How does it work? An air conditioner picks up heat from somewhere that we don't want it. So the somewhere that we don't want it in this case is the warm, unconditioned air that's coming through the return. It's hopefully being filtered as well. So that's where you're going to clean up your air is in the return. Return means it's coming back to the system, and then supply means it's going to the conditioned space, supplying the space. One thing you need to understand about air conditioning is you're not just blowing cold air in, you're also taking warm air out. And so I always use the example of it's like filtering dirt out of if you had a bucket full of dirty water, and you were trying to get the dirt out of it, and you were going to run it through filters. Maybe you had a pool, swimming pool, be a good example, and you were going to try to run it through a filter and remove all the dirt and the stuff you didn't want in it. And so in this case, the air would have stuff we didn't want in it, being moisture and heat, unwanted heat. So if you ran that through a filter, you pull it in through the skimmer, and then you run it through a filter, you run it back out, um, and it's hopefully clean of some of the debris and the stuff that you're not wanting to be in there. So in this case, the stuff that we're not wanting to be in there is heat and moisture. So um, remember, we're not just cooling a space, we're conditioning a space, which means we're getting the moisture, the humidity in the right ballpark, and we're also getting the temperature down to where we want it. So you return your supply. Outdoor unit, you've got outdoor ambient air, which is just the air around the unit, and then hot air coming out the top. So the air at the top of this unit should be warmer than the air at the side, or the air coming in the side. As long as it's a type that pulls in air. There are a few out there that push through it. Most of them pull air through. So air will be coming in through the side and then going out the top. So if you're removing heat from the house, ultimately that heat will be rejected outside, and you can tell that by sticking your hand over the top of that fan. Um, but in order to get rid of that heat, it actually has to transfer that heat several times and change its states and change its pressures. So that's where your refrigeration circuit comes in. Hopefully, you understand at this point a little bit more about the difference between latent and sensible heat. You understand that refrigerant has a saturation point. You may not exactly know what that means at this point compared to water or something. What we might would think of having a saturation point, a boiling point. So the boiling points of refrigerants are a whole lot different, especially when they're inside of the system. So that's where your PT chart comes in, your pressure temperature chart that you have access to and that you've been hopefully using, and your gauges have a PT chart on them as well. So remember, you just got to find the temperature, define the pressure, and the refrigerant that you're using, match that up on that chart, and that'll tell you the temperature, the saturation point of that refrigerant at that pressure, or vice versa. If you know the temperature, then you can find the pressure. Not going to spend a ton of time going back on that. So that's kind of where we're going to get to, but before we go there, we got to start here. Uh, Basic refrigeration circuit. You can see this drawn different ways. You'll see me draw it in class a little bit different. It may go left to right, right to left, depending on how I decide to draw it that day. But this is your refrigeration circuit, and you're going to see me draw this or reference this time and time and time and time again. So if you don't get this the first time, that's fine. There's a lot of things going on inside the circuit. We're going to go over the basic of it right now, and then we're going to add things to it over the next, in every refrigeration class that you have, we'll be adding some things to it. So if you understand this, this is the basis of everything that you're going to do in refrigeration. So every refrigeration circuit has a high side and a low side. They have some sort of evaporator, some sort of condenser. For right now, let's just stick to the basic air conditioning split system, which is this one right here. So that basic air conditioning split system is going to have an outdoor unit and an indoor unit. It's also going to have some sort of blower that moves air across an evaporator. So that evaporator is where your heat is going to be captured. And then your outdoor unit has a coil around it, or in this case, it's kind of over here on the side just to show you. That coil is your condenser coil, and that's where the heat's going to be rejected. You've also got a compressor. That compressor is taking in refrigerant, compressing it like an air compressor would do to air, building its pressure, and then creating flow. So that's the heart of the system. That's the thing that's pumping. That's the thing that's moving refrigerant. So without the compressor, you got nothing. So when your system's sitting there dead, nothing's working, you're going to be at what we call standing pressure, which is just lines full of refrigerant. But once the system starts up, your compressor is going to have a low side and a high side. It's going to have an inlet and an outlet. So imagine that you have a water pump that is sucking in water, and then it's blowing it out a lot harder. A fan does the same thing. So it sucks air in, and then it increases its velocity, or in this case, increases its pressure. So there's different places you can start on this. Really, it's a cycle, so you can start anywhere. But I actually like to start. Most people start at the compressor, but I actually like to start at the evaporator because that's the thing that's actually removing the heat from the house. And honestly, I'll probably come back through this circle again, just so you know that when the circuit starts all over, what it's doing again. So the evaporator. So what goes on inside of the evaporator that causes it to pick up heat? Well, how does heat travel? Heat travels from hot to cold, right? It's from a place that's warmer to a place that's cooler. So if the air in the house is warmer, in order to pick up heat from it, we have to make some sort of coil or some sort of thing that is going to attract that heat. And in order to do that, it's got to be colder. So that's the first rule. The evaporator has to be colder. Now, how much colder? That's going to depend. In a residential split system, AC system, just regular AC, you're looking at that coil being above freezing. Usually, you're going to run about a 40-degree coil. Now, what does that mean? Does that mean the surface of the coil is actually 40 degrees? No, not exactly. We're referring to saturation temperature. So, on your gauges, when you're looking at your gauges, if I ask you how cold is your evaporator or what's your evaporator temp, I'm referring to the saturation temperature. What's going on inside of that? What's the temperature of the refrigerant in that low side? So when I say it's a 40-degree coil, I don't necessarily mean you're going to put a thermometer on it and measure the coil. That's not how we tell that. So how we tell that is by putting our gauges on it, measuring our saturation temps. So kind of get back to that in a minute, but it's going to be colder. So that's the main thing. Evaporator has to be colder. Condenser has to be warmer. So we'll get to that in a minute. But evaporator has to be colder. It has to be above freezing in an air conditioner in order to avoid freezing water to it because it's attracting moisture as well. And it also has to be going through a latent change. Most of it does. So in order for it to actually catch the most heat, as we've seen in our previous labs, um, that evaporator has to be going through a latent change of evaporation in order to absorb the most heat. So the latent change of evaporation absorbs about 1,000 times more heat than the same exact temperature, just sensible. Sensible just means it's measured with a thermometer, count, degrees that you can measure. So if you have a coil that's 40 degrees, but it's not going through any sort of latent change, it's not going to absorb a lot of heat. So remember the example I gave earlier of you have ice trays that are full of really cold water, and you pour one of those ice trays full of really cold water into your coffee. It's not really going to add much, it's not going to take away much heat. But if you take the same size ice cube, but it's ice, because it's got to go through a latent change, it has the ability to remove a lot more heat. So same thing here. It has to be going through that latent change the majority of the time. So I'll go back to this picture here, and you can kind of see that your refrigerant is coming in. It's coming down here on the bottom by the TXV here. So on number 14, that's where I'm going to start. That's your evaporator. That refrigerant is coming in, and the state of that refrigerant leaving that metering device is a saturated vapor, which means it's sort of like a mist. I use the example, it's kind of like a spray bottle. You got like a Windex bottle or something, and you're spraying, and so there's water in that bottle or there's fluid, and you spray it, and if you spray it, it's going to mist. It's not just squirting it straight out, but you spray it on your arm's going to get wet. You spray it on a window, that window's going to get wet. But there's also air; it's aerosolized. So because it's a mix, it's already starting in the process of changing states. So what the evaporator does is it picks up heat, even though it's cold, it's 40 degrees, but it's going to start going through the boiling process. So the refrigerant at whatever pressure that's going to be, that coil needs, so our job is to get that coil to the desired temperature. So we don't react to what the system's doing so much as, we try to make the system do what it's supposed to do. So that coil should be, in this AC system, it should be around 40 degrees most of the time, just as a general rule. To make that even a little more accurate, it should be 30 to 35 degrees colder than it is inside or than your return air is. So if you've got 75-degree return air, you're going to have a 40 to 45-degree coil most of the time. So there's a rule of thumb that you'll hear me say: indoor minus 30, outdoor plus 20. So I'll get to the outdoor part in a minute, but this is your indoor minus 30, indoor minus 35. That saturation temp of that refrigerant should be 30 to 35 degrees below indoor temps, your return air temp. So you're blowing air across it. It's going through a latent change, but why is it going through a latent change? Well, it started as a mist, but if we don't enact any other heat upon it, it's going to just remain a mist, right? So why is it going through a latent change? Well, it's going through the latent change of evaporation, which means it's becoming a vapor, which means it's boiling, and it's going to eventually become 100% vapor before it leaves this coil, or it should. It's doing that because it's picking up the additional heat from the house. So if you've got 75-degree air coming into this room, or in from the room into this return, you're pulling it across that coil, and that coil's cold, and it's going through an evaporation process. So it's picking up heat like crazy. It has the ability to move heat. Plus, there's fins in that. Imagine it's kind of like a radiator on a car. So those fins slow down the air, and they're made of metal, so they're really conductive for heat. So all of that works together for that heat to be trapped and go from the airstream into the refrigerant stream. So that's a transfer of heat. Heat from the air to the metal, from the metal to the refrigerant, and then from the refrigerant through the refrigeration circuit to eventually go outside. So as a result, the refrigerant evaporates because it had heat from the house added on it. So for example, if something were to happen that your filter got dirty or your fan stopped blowing, it's no longer going to evaporate anymore. So we'll get into that when we get into troubleshooting. You'll see that and how we can test for that. But if you lose your fan, you got no heat moving, then nothing's going to change that. You're not going to evaporate, and you're not going to get 100% vapor out of that coil. Now, why is that a big deal? So moving on to the next step. It leaves the evaporator and it goes to the compressor. So at this point, this is our low pressure side. So it leaves the evaporator, it goes to the compressor, and it at this point it is 100%. I've got to go check something. You may hear a noise here, but it's 100% low pressure vapor. So this is what we would call suction gas. This is our excuse me, I'm actually canning beans back here in the room, so I've got a pressure cooker, right? As pressure increases, temperature increases. So canning green beans. But anyway, so at this point you have 100% low pressure gas, 100% gas, or you should. There's multiple reasons why the compressor should never see liquid. And one of the main reasons is it's going to damage it. There's a couple of different ways that it can. I'm not going to get into that too much, the details of that, but two reasons why liquid refrigerant can cause the moving parts to actually break or cause them to be damaged. And one of the main reasons is you get what you call liquid floodback or liquid feedback, to where you actually have that refrigerant going in and mixing with oil in the bottom of that compressor. So in this compressor, there's oil in the bottom of it and in the crankcase, just like there would be in a car engine. So you got moving parts in there that need to be lubricated. That liquid refrigerant, if it works its way into that compressor, liquid refrigerant will mix with that oil and can migrate that oil out of that crankcase, which then takes away the lubrication of those moving parts and can cause them to break down a lot quicker. So you don't want liquid back to the compressor. So at this point, it's low pressure vapor coming in, going into the compressor, and at this point, it gets compressed. Well, what does that mean? Uh, well, basically, its pressure gets raised. It gets um, its pressure gets raised, its temperature gets raised, it goes to a higher temp. It doesn't change states at this point. So you'll notice it comes in as a low pressure gas and it goes out as a high pressure gas. So this is what I would kind of commonly refer to, and a lot of people do, is hot gas, your hot gas line, or discharge gas. So you're discharging that refrigerant as a 100% hot gas. Um, it's very, very hot. I mean, this could be 100 and 165, 175 degrees at times. I think I'm trying to think of the limits on that, but it can be very hot. So if you're touching a hot gas line, which honestly you don't really have good access to on an air conditioner, now in heat pump you do, but if you're touching that, just be careful because it can be pretty warm. Um, so it's leaving that and it's going as a hot gas. So you'll notice, you'll follow this along from 3 to 4. Um, and this is a heat pump, so it's kind of going through this reversing valve, which really doesn't mean anything to us right now. It goes on through that discharge gas, and it gets to the condenser. Well, at the condenser, what's it doing? So once we compress that heat, or compress that refrigerant, why do we compress the refrigerant? Well, hopefully you kind of see the relationship between hot going to cold and pressure and temperature being relative. So if I have to get the coil colder inside to attract heat to it, what do I have to do outside to reject heat from it? I have to get that coil hotter. Well, how do I get it hotter? By increasing the pressure, right? Because if I increase pressure, I increase temperature with it. So I increase the temperature of this coil, knowing that even if it's 100 degrees outside, that's fine because my coil will be warmer. So you heard me earlier say indoor minus 30, outdoor plus 20. That's just a rule of thumb, but it gets you an idea of how this thing's working. So the inside has to be colder. The refrigerant temperature has to be 30, 35 degrees colder. The outdoor refrigerant temp has to be around 20 degrees warmer. Now, higher efficiency systems will run at a lower temperature split. So instead of 20, it might be 15 above. Older systems may run more like 30. So that can be a little bit more of a wide uh, range depending on the efficiency of your system. But just for this case, let's just say it's outdoor plus 20. So if it's 120 or 100 degrees outside, you're going to be running like 120-degree refrigerant temp outside your condensing coil. All right. So once it gets to a high temp and a high pressure, then it starts to condense. Well, why does it start to condense? The same reason the evaporator started to evaporate, because you're moving air across it. Well, how are we moving air across it? Well, inside we moved it with a blower. Outside we're moving it with a fan. Uh, Fan's going to pull air across that coil. It's going to pull that air through the coil and outside, the same way that the fan inside did, pulling it across those fins. Uh, that heat is being attracted to the colder thing. Inside, the colder thing was the coil itself, the refrigerant. The outside, the colder thing is what? It's the air, right? So if it's 95 degrees outside, you may think, well, that's really, really hot, right? Well, remember what I told you. Everything is relative. So even if we think 95 degrees is hot, 95 degrees is cool when we compare it to 120, right? So if we get that refrigerant temp up to 120, and the air coming across it is 95, where's the heat going to go? Heat's going to go with the colder thing. Well, what is the colder thing? It's the air. So that air is going to come through, go across, and as a result, the heat is then going to be transferred back from the refrigerant, out of the refrigerant, back to the air outside, right? So what's the process? From somewhere that we don't want it to somewhere that we don't care. So at this point, we picked up the heat and we got rid of it. So for all intents and purposes, we're done, right? But we have to go back and start the circuit over, because remember, it's just like filtering that water in your pool. The more times you filter it, the more stuff you get out, right? You don't just run it through once and kick it off. Um, so back to our picture. So it goes to the compressor as a high pressure gas. It goes to the condenser as a high pressure liquid, right? So most of the change isn't sensible. It's mostly latent, which means that most of the heat is released because that compressor is going through the latent heat of condensation. So it's losing heat, therefore it goes back to a liquid. Once it becomes 100% liquid, it goes to the what? So what's the next thing on your picture there? The metering device, expansion valve, piston, orifice, TXV, EXV, EEV. There's a lot of different types, float valves and chillers, a lot of different types of metering devices. But a metering device is not like, you're not going to go to a store and say, I need to buy a metering device. Um, it is a device that meters refrigerant. So that's kind of a general term. There's different types of metering devices, but that's basically its generic term. So in this case, they're calling it an expansion valve, but for whatever thing, it's kind of like the Windex bottle, the nozzle in the Windex bottle that we talked about. It's going to take in that liquid refrigerant and it's going to restrict it through a little tiny opening to where it sprays out. Well, that spraying out is what I would call, and a lot of people call, like flashing or flash gas, flashing off, to where it is giving up some of its liquid properties and becoming more of a mist. So we said when it comes into the evaporator, it's a mist. It's a liquid vapor mix. So think about that spray in that bottle. That's what that expansion valve does, or that metering device does, is it restricts it to the point that it starts to break down. Well, as a result, not only does it start to break down, but it also reduces its pressure. So if you can imagine, you've got all this pressure, this liquid pressure coming to that piston or that TXV, and it's meeting a roadblock. So I like to think of, I'm an analogy guy, if you haven't figured this out. So imagine that you're driving down the road and all of a sudden, you're going 85 miles an hour down the interstate and everything's fine, and all of a sudden you hit a roadblock, or you hit traffic, or you hit a toll booth or something, to where you have to come to a stop. Traffic has to come to a stop. Well, now all that traffic's backed up on the backside, but on the leaving side, the pressure is a lot less because only a few people are getting through, right? So this is where our pressures split back. So you'll notice that splits, right to left, high side, low side. The expansion valve is where it goes from high to low. It comes out, it comes into the expansion valve as a high pressure liquid. It comes out as a low pressure, and there, this says low pressure liquid. I would say low pressure saturated vapor, low pressure mist. Um, and then it goes back to the evaporator. So back down to our picture. The liquid line should be full of liquid, 100% full of liquid. Why? Well, imagine if you took that bottle of Windex and you sprayed that on a window, right? And then you got in kind of a weird spot and you were trying to get it somewhere else, and you turned that bottle upside down and that straw's on the bottom. Now I know they make a nozzle that'll fix that, but let's just say you don't have that nozzle. So the bottle's upside down, the straw's up on the top now, and it's sucking air. Are you going to get any stuff out? Nope. It's just gonna kind of sit there, right? It's not going to do anything because it has to have access to 100% liquid all the time. So once the bottle starts getting empty, you start kind of sucking air, and then you have trouble getting the liquid out of the bottom because you've lost your suction. So it's the same thing with this. It has to have a steady stream of liquid. Uh, so there's ways that we ensure that that condenser is completely condensing 100%, and we'll get to that later. It goes through a filter dryer normally somewhere in the liquid line. I like to have that as close to the TXV as I can, just to protect it. The filter dryer's purpose is just to filter the refrigerant, just in case there was something that would make it into the system or through the system before it gets to that little tiny opening. Hopefully, because that's the thing that can get stopped up pretty easy. That filter dryer is going to catch that. So, all right. So that is your refrigeration circuit in a nutshell. Probably the fastest I've ever covered it. Here's another picture of it. Sort of breaks it down another way, but hopefully you at least understand that a little bit, and we'll definitely build on this. So understand this. It's not the last time you'll see it. So that'll do this. That'll do it for this one. In your lab, you're going to be asked to identify some of these components, and some of your labs you're going to be actually hooking gauges up and measuring pressures, and then we're going to go on from that and use those pressures and temperatures and some other readings that we're going to learn how to take as diagnostics. Maybe not so much in this class, but especially in your 250 class next 8 weeks. So if you don't know how the system should work when it's working right, it's really hard to diagnose when it's not working right. So we're going to drive that in your head. So start understanding this now. Take the initiative at this time. This is a really good time to go find more things. So don't look at this as an opportunity to say, what's the minimum I can get by with? Because if this is what you want to do for the rest of your life, then you better understand this. This is a really, really important concept. This is the basics of what you do. Electricity is going to be the same way. If you don't understand what your gauges should say or what your meters should say, what difference does it matter what they do say? You have to be smarter than those tools. So we're going to teach you how to know what your gauges should say before you ever look at them. And then all you're doing is verifying that it's what you expect it to be. So stick with me, bear with me, and we will get you through this. It's not bad. It's not as complicated as it seems, but it's pretty cool. So see you later.